Welcome back to 10-Minute Science. Last time, a single neuron learned to predict a house price from its size. One weighted sum, and out comes a single number. But what if the answer isn't a number? Is this photo a cat, a dog, or a bird? That's a category. So, what should the network output? The obvious shortcut. Keep one output and round it. 0 is cat, 1 is dog, 2 is bird. The marker snaps to the nearest. Simple, but look what it quietly assumes. But that sneaks in a fake order, as if dog sat between cat and bird. They are just names, with no order at all. A single number is the wrong shape for this answer. So give every class its own score. 3 classes, 3 weighted sums. We call these raw scores the logits. Watch them spring out. The cat already leads. But what exactly are X and W here? Let us unpack them. Start with the input. Remember the house, its size, its age. Each one a single feature the model reads. A picture is no different. Look, each pixel is just a feature, and how bright it is, that is its number. Now stack every pixel into one tall column. That column is the vector X. Watch how many slots it has. That count is its dimension. This little patch is tiny. A real photo? Hundreds of pixels, hundreds of dimensions, all fed in at once. So how do those numbers turn into scores? Through W. Watch. Every feature reaches out to every class, all at once. Each score listens to the whole picture. When everything connects to everything like this, we call the layer fully connected. Every single line carries one weight, one dial the network can turn. Put them all together, and that is thousands of dials in this one layer alone. This whole grid is W, and training is just the slow tuning of every dial until the scores come out right. So back to those 3 scores. Can we read them straight as confidences? Not yet. Look at the problems. A score can go negative, it has no ceiling, and together they do not sum to 1. Real probabilities each sit between 0 and 1, and together they cover everything. The fix is one operation, Softmax. It works in 2 clean moves. Move 1. Raise e to the power of each score. Watch each one climb the curve to its bar. E of anything is positive, so every score comes out above 0. The negative score problem is gone. And because e to the x climbs so fast, a small lead becomes a big lead. The gap between the top 2 widens, but the order never flips. Cow is on top, cat stays on top. Move 2. Add up all 3 and divide each by that total. Every bar drops into the 0 to 1 range. Now watch. Every bar lands between 0 and 1, and together they sum to exactly 1. A real probability distribution at last. This recipe has a name, Softmax. Each score goes through e to the power, then we divide by the total. One practical warning. Real scores can get large, and e to a large number explodes past what a computer can store. It overflows and the math breaks. The fix is simple. Subtract the biggest score from all of them first. Softmax only cares about the gaps between scores, so shifting them all by the same amount changes nothing. The probabilities come out identical. But now every exponent is 0 or below, so the numbers stay safe. Every real Softmax does this. Reading the answer is easy. Pick the biggest. Cat, 66% wins. And that number is the confidence. The network is 66% sure it's a cat. We keep all 3 numbers, not just the winner. They show the network was a little torn between cat and dog. That soft confidence is exactly what we grade next. The true answer we write as a one-hot vector. Y. Cat gets a 1, dog and bird get 0s. That's our ground truth, and we'll use it to measure how wrong the network was. So, how wrong was the guess? Before any formula, let us be clear on what we even want. It is simple. The true class should get a high probability. Push that number up on every example. That is the whole goal, but a loss is something we push down. So we flip the idea into surprise. Watch the When the model is sure and right, surprise sits near 0, no penalty. But when it nearly ruled out the truth, surprise rockets up. A confident mistake shocks it the most. This surprise even has a unit, bits. Watch the steps climb. Each time the truth gets half as likely, the cost goes up by exactly 1 bit. Rarer truth, more bits. And our loss is simply the average of the surprise. Why a log, though? Why not just measure the gap? Watch both lines. The plane gap barely moves as the model gets it wrong. But the log curve explodes. That is the point. A confident mistake should hurt, and the log makes sure it does. Now connect the two. As the true class climbs towards certainty, watch the surprise slide down to nothing. Making the right answer likely, and making the loss small, they are the very same goal. Written out in full, this loss has a name: cross-entropy. It looks like it adds up every class, but remember, the true answer is 1 hot. Watch the other terms. Multiplied by 0, they simply vanish. All that survives is the surprise on the true class. Back to our cat. We were right, but not certain. See where the dot lands: a small loss, a gentle nudge. A good guess, the model says, but you could be sure. Now, the bad case. The network is certain, and certain it is a bird. Watch the dot climb the cliff. The loss explodes. That is cross-entropy doing its job, punishing a confident mistake without mercy. Softmax answers. Cross-entropy measures the error. But why this exact pair? Watch what happens when we try to improve. Nudge a score. Does the loss rise or fall? That is the gradient. And it is beautifully simple. The gap between our guess and the truth. See the arrows? Each score is pushed straight toward the truth. The error itself points the way. Let's put it together. Raw logits. Softmax makes them probabilities. The biggest is the decision, its value the confidence. Cross-entropy grades it, punishing confident mistakes. And predicted minus true says which way every score is wrong. But we took one thing for granted: the weights that made those scores. We know the error and its direction, not yet how to push it back through the network to change the weights. That's backpropagation next.
See you then on 10-Minute Science.